In this Aspire demonstration movie, we'll demonstrate native code diversity in space. You might remember this chart from the introduction to the project, where we showed that we want to increase the effort of an attacker to engineer an attack, that is, to identify an attack vector. We want to delay him by deploying protections. That was the first goal of our protections. And then the second goal that we want to reach actually with diversity is to minimize the blue area here, the profit that an attacker can make, and diversity can play an important role here by lowering this curve. If we distribute different versions of the binaries to different customers or end users, engineered attacks will not work on all of them. At least that's what we aim for. There are also other goals of diversity, like decreasing the learnability and decreasing the possible reuse of previously obtained knowledge from an attacker, but we'll not discuss those in detail in this video. Now, how do we generate diversity in native code? Well, it's very simple. You might also remember from another video that we deploy control flow obfuscations, so we can insert opaque predicates. We can apply control flow flattening on the graphs of our functions, and we can insert branch functions, so that's to redirect the direct control flow by indirect control flow. And what we'll do to generate diversity is to apply those stochastically. So we'll use a pseudo-random number generator that will decide where the control flow obfuscations are applied, and I will use different seeds to generate different versions. If the pseudo-random number generator that decides on the locations where the transformations are applied, if this is initialized with a different seed, we'll get different versions. And to control the level of diversity, it suffices to control the frequency with which we apply the transformations. Furthermore, we'll also use those random seeds to randomize the code layout. And the reason is that with these obfuscations, disassembly tools like IDEPRO cannot reconstruct functions by just looking at the control flow, but they might still be able to do that based on the code layout. In a normal binary, the code of each function is stored consecutively in memory. But by randomizing the code layout, also this form of information is gone, and it's only if the two forms are gone, being the direct transfers in the original program that have been replaced by indirect ones, and the layout that's gone, then a tool like IDEPRO can no longer easily disassemble the program, and then tools on top of the disassembler, like BinDiff, they can no longer match functions in multiple program versions. And so that's where we're going to break collusion attacks, or we're going to prevent that attacks are repeated automatically on different versions of a binary. In the Aspire project, we deploy these protections on the binary code, and so we transform the program at link time using Diablo, the link time rewriter developed at Ghent University. Of course, there are also alternatives to generate diversity. In particular, source level transformations can be used. For example, one could reorder the fields in structs or reorder parameters in functions, and there are tons of other transformations that can result in different versions of binaries. We have not implemented tool support for those source level transformations in our project, but ideally all of them would be combined. In the previous slide I mentioned tools like IDEPRO and BinDiff, but there are also other attacker tools like pointer chasing tools, of which the usefulness will decrease if the program is diversified. Now let's look at the practical result of using these techniques on a real-world program with our toolchain. We'll do that with a demonstration. So here we have two terminals in our development VM. Notice that we have two different directories. And in both directories, we'll compile and protect bzip, the well-known compression utility, with our toolchain, the ACTC. In the link time rewriting step, a pseudo-random number is generated. And amongst others, this number is based on a hash of the directory in which the code is compiled. So for the two compilations and protection runs, different random seeds will be used, and hence different binaries will be generated. I will speed up the compilation processes because they take a while. But after the compilation is done, we can open IDEPRO on the two programs. First here we see the disassembly process of IDEPRO on the first binary. We save the result in a database. Then next we disassemble the second file. Now, once this disassembly process is done, we can invoke the BinDiff plugin in IDA Pro, and we instruct this plugin to compare the currently disassembled program against a program that was already disassembled and of which the result was stored in a database. So we open the database that we just created, and we ask BinDiff to compare a diff between the two binaries. This takes a long time, even though in this case we applied the diversification quite minimally. For this demo, we asked our link-time rewriter to deploy opaque predicates and branch functions and so on a random basis in relatively few places in the program. As a result, the binaries differ not that much, but already the diffing takes a very long time. So I'm going to speed this up. If we would have instructed our toolchain to deploy these random transformations more frequently, BinDiff would just fail and crash. Then we would not be able to demonstrate the result, so that's why we only used kind of light diversification. Still, I have to fast forward BinDiff's operation. I'll do that now. So now the diffing has ended. First, we see that in the second program, there are still many functions that IDA Pro has identified, but that have not been matched to functions in the primary program. So apparently, BinDiff was not very successful in finding matching functions. Also, if we look at the primary unmatched functions, we see there are plenty of them. Then, if we look at the functions for which IDA Pro was able to find a match between a function in the first binary and a function in the second binary, we see that it has been able to match quite a number of functions, and for many of them, shown here in green, IDA Pro is very confident. That's of course because in those functions no diversification was deployed at all. But we see that there are also many functions, you see them here in orange and then in red. You see here many functions for which IDA Pro indicates it might have found a match, but actually, if you look at the similarity numbers on the left, you notice that the similarity is extremely low. And if you look at the features of these functions, like the number of blocks, the number of matched basic blocks, you see that in many cases these matches are actually not correct, or at least not completely correct. So you see that even with light diversification, we have been able to fool the diffing tool. The Aspire project has received funding from the European Union 7th Framework Programme under Grant Agreement number 609734.